This is a projectile motion problem. Parts A and B do not require any trig or vector addition. Part C does, so I'm going to solve parts A and B first, and then we'll solve part C. Solving for part C won't always be necessary for all problems, but we're going to do it for this one. Let's take a look. A 55 kilogram cannonball is fired horizontally from a 140 meter tall vertical cliff. It lands 440 meters away from the base of the cliff. Air resistance is negligible, and G equals 9.81 meters per second per second. So for any projectile problem, the first thing we want to do is draw a diagram. It's fired horizontally from a cliff. So that means the trajectory is going to be, well, it's always going to be a parabola, but it starts out moving horizontally. Eventually it hits the ground. It's fired with some initial velocity to the right. And since our initial velocity is just horizontal, it's only in the x direction, I'm going to label that Vx. We know that the distance that the object falls, or the displacement that the object falls, is delta y. However, actually we are given delta y. Delta y is going to be 140 meters. 140 meters. Delta x is the horizontal distance that the object travels. Delta x in this case is equal to 440 meters. Air resistance is negligible, and G equals 9.81 meters per second per second. We also know that it is going to hit the ground with some final velocity. And I'm going to keep everything broken into components, so our x velocity is still going to be Vx. Our y velocity is going to be some downward accelerated velocity, Vy final. So next up we need to set up our table of variables. We have our x variables, our horizontal variables. And our x variables are Vx. Since velocity is constant, Vx is always the same. We have delta x, displacement in the x direction, and we have time. In our y direction we have Vy initial, Vy final. We have acceleration in the y direction, displacement in the y direction, and time. Now before we start filling in our givens, let's choose our positive direction, and I'm just going to be pretty standard and choose right to be positive and up to be positive. If that's the case, then my displacement over here, delta y, in the y direction, is negative, and my x displacement is positive. So we can fill in what we know in either direction. Vx, we are not given, we don't know what it is. Delta x we are given, it is 440 meters. Time in the air we are not given, that's what we need to solve for in B. V initial y, we are not explicitly given, but we do know. The projectile is fired horizontally, which means that its initial vertical velocity is 0. Our final y velocity we don't know, but we do know that for projectile motion near the surface of the Earth, the acceleration is always constant. It's always equal to g. So it's going to be equal to 9.81 meters per second per second. Gravity's pulling it down. And since gravity is pulling it down, it is a negative 9.81 meters per second squared. Oops, that's in the wrong column. Minus 9.81 meters per second squared. Displacement in the y direction is also given. If it is launched off a 140 meter cliff, it travels down 140 meters before it hits the ground. So our y displacement is minus 140 meters. Time is still unknown. So we have two unknowns in the x direction, which means we cannot solve for everything. Two unknowns and one given. But in our y direction, which I didn't actually label, let's label that here, y, we have 3 givens and 2 unknowns, which means we can use our kinematics equations to solve for our other variables in the y direction. In part A, we need to find the initial velocity of the projectile. So since it's launched horizontally, our initial velocity is just going to be vx. However, to solve for vx, we're going to need the time. And we can't solve for time using the x component of motion. So let's look at the y component of motion. In the y component of motion, we do have enough variables to solve for our time. So we need to choose the correct kinematics equation that has Vy initial, Ay, delta y, and t in it. And that equation is going to be right here. Let's do it. Solving for time. We can use delta y equals v naught times t plus 1/2 a t squared. We know that our initial velocity is 0, so this whole term goes to 0, and we end up with delta y equals 1/2 ay times t squared. Divide both sides by 0.5 ay divided by 0.5 ay. You get some cancellation on the right. We're going to be left with delta y over 1/2 a is equal to t squared. So to solve for t, we need to square root both sides. And we end up with t is equal to square root of delta y over 1/2 acceleration in the y direction. We can plug in our numbers. Delta y is equal to negative 140 meters, divided by 0.5 times negative 9.81 meters per second squared. If we plug that into a calculator, we get 140 over 0.5 over 9.81. Take the square root of that. We get our total time in the air as 5.34 seconds. And so we've solved for our time. I'm going to fill that in on the table in blue. 5.34 seconds, 5.34 seconds. So we solve for the time in y. That gives us the time in the x direction as well. So we can use the time in the x direction to figure out our x velocity, vx. So let's do that. Let's do that down here, solving for vx. Since our x motion is constant velocity motion, we get delta x is equal to vx times t, displacement is speed times time. If we solve for vx, we just get vx is equal to displacement in the x direction over time. So that's going to be 440 meters, positive 440, over 5.34 seconds, which is equal to 82.4 meters per second. Great. We've solved for Vx. I'm going to fill that in the table. 82.4 meters per second. So if we go back to our problem, we needed to find the initial velocity of the projectile, Vx. So I'm going to just put a little solution box over here. Solution. Vx is equal to 82.4 meters per second. And in part B, we needed to find the total time the projectile is in the air. T is equal to 5.34 meters per second. Part C, our last part, asks us to find the final velocity of the projectile just as it hits the ground, and it wants the magnitude and the direction. Now, just as the projectile hits the ground, it has both a horizontal velocity and a vertical velocity. It's accelerated down in the vertical direction by gravity, and it still maintains its constant horizontal velocity. So if we want to find the resultant, or the overall final velocity of the projectile, we need both the x velocity and the final y velocity. So since we're looking at the final y velocity, we're going to need to look in the y direction to solve for that. So let's move over to here and solve for v final y. Finding Vy final. Well, we need an equation that has Vy final in it. So I'm just going to use our this kinematics equation, V final equals V initial plus acceleration times time. That's already solved for V final for us. So it's going to be pretty easy to plug in our numbers. V initial in the y direction is 0. Plus our acceleration is negative 9.81 meters per second squared. And our time in the air is 5.34 seconds. Which means our final velocity in the y direction is just equal to negative 52.4 meters per second. And I'm going to fill that in my table. Negative 52.4. Negative 52.4 meters per second. And that negative sign is important. It tells us that our final y velocity is in the negative direction, which means our object is moving down just as it hits the ground. It's traveling down. But that doesn't give us our final velocity. To get our final velocity, we need to figure out the resultant. So we're going to draw a vector triangle with our zoom out a lot, with our x and our y final velocities. We know that if we sum up, let's actually just go over here. If we sum up the vector for the final x velocity, which is to the right, v final x, we add it to the vector for v final y, our resultant is going to be the final velocity. And let's just make that a little bit more. To scale. Our v final x is just vx. It's 82.4 meters per second. Vy is a little bit less. It's negative 52.4 meters per second. I'm just going to put the magnitude here, 52.4 meters per second. And my resultant, v final, is right here. And the direction is going to be that angle from the horizontal over here. So we can just use the Pythagorean theorem to find v final. V final squared equals v final x squared plus v final y squared. If we take the square root of both sides, we get v final squared is equal to square root of, well, 82.4 squared plus 52.4 squared. I'm omitting units just to make it easier. Oh, and I accidentally added an extra square on my v final, so let's get that erased. We plug it into our calculator, we get v final is equal to 97.6 meters per second. That gives us the magnitude of our final velocity. If we want to find the direction, we need to use an inverse trig function. Since we know all three of the sides of the triangle, we can use any trig function we want. I'm going to use tangent, inverse tangent. So theta is equal to inverse tangent, or arctan, of the opposite leg, which is v final y, over the adjacent leg, v final x, which means it's going to be inverse tangent of 52.4 over 82.4. We plug that into our calculator. And since I want my answer in degree mode, my calculator is in degrees mode, and I get 32.4 degrees. Okay, that's it. We've solved for the magnitude and the direction of V final. Let's just put that in our solution over here so it's easy for whoever grades our work to read. Part C, our object hits the ground with a velocity V final equal to 97.6 meters per second at an angle of 32.5 degrees below the horizontal. There's one example of a projectile motion problem. For a projectile that is launched horizontally off of a cliff. We're just applying kinematics in both the x direction, constant velocity motion, and the y direction, constant acceleration motion. And if we need to find or resolve vectors into components, we do. If we need to combine components of vectors into resultants, we do. Hope this was helpful. Bye.